Okay, this is a video to show in using chemical models, 3D chemical models, the hydrogenation of butane. Okay, butene, excuse me. So we've got the double bond, butene, right here. Okay, this is 2-butene. This one happens to be in the cis configuration. Okay, with the carbons right across from each other. But this reaction would proceed the same way if it were in the trans configuration, maybe just with a different reaction rate. Okay, now what I've been using is this chemistry book by Timberlake, in which she's talking about hydrogenation, and I've been reviewing that. This particular reaction that I'm talking about here, she shows here as taking butene, 2-butene in particular, to butane, okay, and in the process using a catalyst, in this case platinum. A catalyst such as finely divided platinum, nickel, or palladium is used to speed up the reaction. Okay, so that's the context. What we're going to end up with is the butane molecules right over here. Okay, and what we're going to look at is the mechanism, how that's going to happen. Okay, and one of the things that we first want to mention is that this is taking place in a catalyst on a surface. So in this video, I'm going to use this tabletop as the surface, and in particular, the metals which she mentions as being used for this reaction were nickel, palladium, and platinum. And lo and behold, they're all in the same column on the periodic table. They're transition metals. They have partially filled d orbitals. And that's what makes them a good candidate for this reaction. Now, the reaction will take place even without the catalyst, okay? The hydrogen atom, the energy in the hydrogen atom and the butene with the double bond is higher energy form than the butane. As gases, you would find that the hydrogen molecule with sufficient, collisions, eventually there'd be a collision with sufficient orientation, let's say at the right temperature, with enough energy to overcome the activation energy, could react with the pi bond, which is taking place here. The pi bond is perpendicular to the sigma bond, which is between here. Now, in the molecule kit, you have these bent tetrahedral bonds, which is really kind of artificial. Okay, in this actual bonding, it's sp2 bonding, and you would have p orbitals of each of these perpendicular. Those would be the pi orbitals, and there would be a pi bond between them. And there's an overlap between the p orbital on this and the p orbital on that. Now you can imagine that if the hydrogen atom had the right orientation, that hydrogen atom could form a bond onto one of those, then possibly forming an intermediate, and the complete reaction could take place. The exact mechanism would be, unclear. Only knowing that this has a lower overall energy, you know that it could take place, but because there would be an activation barrier, you don't know the rate. Okay, so for commercial purposes, the idea on this is to use the catalyst to lower the activation energy. And the way this will work is these particular the way it will work is you want the hydrogen atom to actually form bonds, hydrogen bonds or chemical bonds on the surface between the hydrogen atoms and the electron-rich metal. Okay, and you want those bonds to overcome the hydrogen bond itself, so that these now hydrogen atoms, let's say, could quite possibly be free to move around on this surface. Okay, now the idea on this is that a bond between the d orbital in the transition metal cannot be too strong so that it forms a strong chemical bond, and it cannot be too weak that it doesn't form a bond at all. That's the secret behind these particular metals. Okay, it's found that iron, for example, because it has 5 d orbitals, or 6d orbitals with electrons, that it is too reactive. In other words, there's too many electrons available for bonding. And on the other side, copper and silver, because many of the d orbitals now are filled, the number of open d orbitals is smaller, and it's not reactive enough. In this case, the nickel and the palladium and the platinum represent a sweet spot for hydrogen. And these are very successful. These give the maximum of the different metals. The different metals will give you a reaction. It's just that it doesn't have as high a reaction rate. So this is the sweet spot for reaction rate with hydrogen. It's strong enough for the hydrogen to bond onto the surface. It's not so strong that it can't come off the surface, okay? When it's on the surface, it provides a substrate. If it's moving around on the surface, and if the p orbitals of the butene also form some type of a hydrogen bond or chemisorbed, adsorbed onto the surface, that would allow this to move around. This increases the reaction rate because it's taking place in a 2-dimensional surface rather than a 3-dimensional surface. When the hydrogen atom gets into a collision now, this has a smaller activation energy than when it's in the molecule. And therefore, you can get a reaction intermediate, for example, where one of these bonds, let's say, is broken, and you end up with a bond, and you end up, this would now be not an accurate representation, but there'd be some sort of an intermediate structure. Okay. As that intermediate structure eventually comes into reaction with another hydrogen atom, which is on the surface, you could get a completed, let's see, where did I wanted to get a shorter bond, because I want to represent the you want to represent this bond. You know, the length of this bond is not accurate to begin with. It's only in there because it bends. When it makes a collision with another hydrogen atom here, the dangling bond in the intermediate, or whatever the intermediate is forming, it's a more complicated structure. We don't have to worry about exactly what it's shaped like. Okay, so I'm just going to get the shorter bond to make this thing a little bit more, a little prettier, okay? And so then after 2 of those happen, you end up with a butane molecule. Now the butane molecule now would have less attraction to the surface. The reason is because the pi orbitals are reactive because they stick out, and they're at a lower energy. They don't represent, they tend to be reactive. Those electrons can be donated. So that's why after it forms, this generally can become free of the surface, okay? This one here was just sitting on the surface for convenience. It was just kind of a prop, okay? Just to show you what the final product would be. This would represent the final product here, okay? So that's all that I really wanted to do in showing the hydrogenation of an alkene to reduce an alkane through a hydrogen catalyst, solid catalyst. Thanks.